I'm really pleased to be here, and I'm really pleased to be among such a great lineup of speakers. I'm really excited about the talks today. And yes, as Rohini said, thank you very much for the introduction. So I'm here to bring greetings from Naturalis Biodiversity Centre and Tilburg University in the Netherlands, where I work. And in this talk, I want to go into a little bit of detail about deep learning for bioacoustics. And a big part of my motivation is, as Rohini hinted, that really some of my long-term goals are that we can use computation and some of the new and increasing powers of computation to really make sense of the sounds that we're collecting, especially as we're collecting more and more and diverse data sets. And so that's what you'll see some of in the talk. So in my talk, I want to start with the state of the art, and then I'll be talking about particular methodologies in deep learning and how we're using them increasingly in different ways for the particular bioacoustic tasks and some of our very difficult data sets. To think about the state of the art, I wanted to sort of come back to IBAC events in the past, so starting from 2015, which was my first IBAC event in the beautiful city of Murnau in Germany. So thinking back to what did I think machine learning was for bioacoustics back then and how things changed. I attended IBAC in Germany, and I was talking about a method using unsupervised feature learning and random forest classifier. Now, both of those for bird species recognition are essentially superseded by CNNs, that's convolutional neural networks, and those are CNNs now essentially perform both of these tasks in one. So we can see that things have really changed since 2015, at least in terms of what I think is the method to use. I will say that random forests are not entirely superseded. They are good machine learning tools still. But for spectrogram-based machine learning, CNNs are, ever since 2016, certainly been very popular. In 2017, we had IBAC in the fascinating city of Haridwar in India, and I was talking and thinking then about robust generalization of machine learning, and that's why we introduced the bird detection challenge. So the state of the art then was to use CNNs, and by that point it's quite obvious that this was a great tool for spectrogram-based machine learning, and also data augmentation, which is a type of tool for artificially expanding your training data. You can apply that to spectrograms. Then in 2019, in the English city of Brighton, we were thinking about small data sets. And again, CNNs with data augmentation was still a good tool to use. And at that point, there was some interesting work on pre-training, so using other data sets to train your machine learning in advance of using your own system. Now, it was pre-training from image data, I remember, which was a slightly strange thing because we don't need now to pre-train on images. There are some very large, very handy audio data sets. So things have changed again since then. And multitask learning was a topic that I talked about a little bit. That will certainly come up in the rest of this talk. Now at IBAC 2023 in the beautiful city of Hokkaido in Japan, what will the state of the art be? I'm looking forward to finding out, and I'm not going to jump the gun. I will make some predictions a little bit later. But I can at least talk about the state of the art right now. So CNNs and data augmentation, those are still good. Those are still the two basic tools that you should be learning about if you're following deep learning tutorial to apply that to spectrograms or to animal sounds. And the good news is that these are pretty much off the shelf now. You can simply take them, CNNs with names such as ResNet, MobileNet, EfficientNet. These are standard tools that you can download from a software package. And data augmentation as well is an off-the-shelf tool that you can apply. You don't have to use programming to implement your own data modifications. These are off-the-shelf tools. So it's becoming easier and easier. And there are also pre-packaged general purpose bird classification algorithms. BirdNet is perhaps one that is pretty well known now because it does species recognition across a wide range of certainly North American and European birds. There are many open questions. I'm not in this talk going to refer to the open questions. I'd love to talk about them because that's, you know, that's where we're doing our research. But there is a review paper which I've conducted. Oh, someone's adding red lines to my slides. Very interesting. So I would say the review paper that I put out earlier this year covers a lot of open questions, as well as the state of the art in deep learning for computational bioacoustics. So I would suggest you have a look there for more about that. But next, I want to get a little bit more into the detail of the methodology. We're going to be looking at deep learning, and what you see on the screen is the classic setup of we have an audio file as input and a class label as the output. Now, this class label could be species, it could be call type, it could be something else. And the blue box is in the middle. This is representation of deep learning. Deep learning is referred to as deep because it's composed out of multiple individual steps of transforming data. So we gradually, in a sense, we gradually transform the audio into the desired information. And all of these steps are trained in one unified process. So we have layers of processing and they're all trained together. What we see depicted on the screen here is kind of the classic approach, supervised learning. We have a data point, here's some audio as input, and a particular class label is the intended output, and we have data sets where we have these annotated. Supervised learning is the classic way to train these things. So the training is optimized specifically for this one classification task. Now I want to talk about embeddings. This is a word you may have heard and you may increasingly hear when working with deep learning. So imagine instead we want to transform our audio into some kind of feature representation, some kind of rich semantic feature representation. I've drawn it here as a coordinate in an imaginary sort of three-dimensional space. It would actually typically be a very high-dimensional space. Imagine 100 numbers describing your audio file. This is a 100-dimensional space, and then we can consider similarity as maybe being proximity in that space. And actually, one of the classic ways to produce this space in deep learning approaches is, in fact, you train your supervised learning system. And as I said, each of these layers is one step of the processing. And then once we've finished training the classifier, we simply chop off the end. So we take off the final layer. And what you get is, coming out of this intermediate layer, we don't get the predicted class, we get some sort of half-digested output. And this is used as a sort of, the classification task here becomes a proxy task to try and not ensure, but in practice to get some kind of semantic representation from this half-digested representation. So an embedding, the word embedding actually comes from text processing originally. It's not necessarily a deep learning method, but I'm talking only about deep learning here. And so you'll often hear about deep embeddings being audio or some other data transformed into some coordinate representation. So it just maps an input data item into a vector coordinate. So it's a lot like we would do with feature extraction. Feature extraction is a very similar process, except this is data-driven. We're not specifying in advance what the features should be. The idea is that we can then use this representation for all kinds of different tasks. Could be similarity measurement, it could be novelty detection, not directly related to that classification task that I told you about, but the hope is that we have some kind of meaningful representation being created. How do we make it even more likely that that's going to happen? Well, this idea of multitask learning, which I referred to, can help. We can train a system in a deep learning setup to satisfy two different tasks. here I've got task A, which might be species recognition. Task B might be call type recognition. And we have this common part of processing and then a different sort of end layer. And so the whole ensemble here is trained as one. So again, it's a sort of a unified training process, trying to satisfy two tasks at once. And the hope there, again, it's a hope, is that by trying to satisfy two tasks rather than just one, we get a richer representation in our embedding. This basic idea is something that's really been taken a long way, especially by the text processing deep learning at the moment. So a lot of the methods that you've seen producing impressive results on interactive text generation, they're very strongly based on this massively multitask learning. So let's come to bioacoustics. In the title of my talk, I refer to difficult datasets, and to some extent, we might say that in bioacoustics, our datasets are always difficult datasets. We have small size, very often unbalanced representation of different categories, unlabelled, noisy background, time varying. These phenomena are pretty much everywhere, and they are also phenomena which violate the sort of classic assumptions of what you need when you want to perform supervised classification using deep learning and have good, robust results. So we still need to work on the method a lot. But let me go back to IBAC in 2019 when Sarab Sethi presented this work that he then published a year later, using an embedding to perform various tasks in bioacoustics. So what he did was he used a deep learning embedding from AudioSet, which is actually just a generic YouTube audio dataset. So this embedding has been produced not from an animal sound dataset, but from all kinds of YouTube videos, essentially. And he showed that the embedding you produce, as in these figures, can be used to infer things such as time of day, time of year, habitat quality, and even species assemblages. And this is really interesting because this gives us the potential to make a lot of inferences from deep learning based analysis without having to perform this incredibly time-consuming work of annotating extremely large data sets in really high detail. So it's a really interesting development that we can do this. But this idea of multi-purpose representations has been developing more and more. And what you see on the screen now is a data challenge from this year. I wasn't involved in this, but it's a data challenge organized by a large team which aim to create audio representations for many different tasks. So each row in this figure is a different deep learning embedding, and each column is a different task that they evaluate the embedding on. So it actually contains lots of speech tasks, lots of music tasks. Here we've got gunshot detection, evaluating these audio embeddings for lots of different tasks. And the good news is that there are plenty of methods that can perform extremely strongly across these massively different tasks. So this includes speech recognition, gunshot detection, music, genre recognition. It's really encouraging that the state of the art is getting this far. But I do have to point out this column on the left-hand side is with all these blue rectangles indicating failure, actually. This column is the bioacoustics task that they evaluated. It's actually beehive state recognition, a dataset from Ines Nolasco, who's now working in my group. And there's actually a technicality behind why the embeddings didn't work for these audio. And it's partly because the audio clips were very long, and the systems weren't designed to handle very long audio. So there is a technicality there, and it's partly a joke, but it's partly true that, you know, bioacoustics datasets remain difficult. we have scenarios that don't quite fit with the assumptions of the systems that are being developed. So we could do this. What you see in the screen here is many different tasks being evaluated. We could set something up for all of our many different bioacoustics tasks. But what I want to talk about in the next section is, instead of just deriving data embeddings from generic classification tasks, there are new methods, that includes new methods used by the authors on the previous slide, to produce better embeddings that we can deliberately control the embeddings to make them useful for the tasks we want them to be useful for. I'm going to talk about the work of my student Ines Nolasco, and she's motivated by this question of individual recognition. Pavel Linhart's chiff-chaff here on the speaker. Is this the same loudspeaker? Is this the same chiff-chaff that landed on his loudspeaker yesterday, or not? And what we'd like to do is to be able to solve this problem in general, not just for this chiff-chaff, but for many different species. It's very useful for various purposes, which I think I don't need to go into here, but of course, we often only have very few examples per individual. So once again, it's very difficult to run standard supervised learning against these things. Now, the first thing to point out is, of course, that these categories form a hierarchy when we're thinking about individual ID. There is taxonomic class, species, and then below the taxonomy, we can also add a layer of classification into the individual. So if we were just considering pipits here on the right, we might have this two-class classification task and think we can't get very much power because we don't have much data, but maybe we can use all of these categories in some way. And the other thing is that if we use embeddings, hierarchies might be a little bit hard to think about in terms of machine learning, but embeddings can handle hierarchies. So we have maybe a kind of hierarchical clustering, which you see in the lower version of the image. And if we can produce an embedding that creates a hierarchical clustering like this, it will be useful for this hierarchical classification task, including individual ID. And then the motivation here is that even though these species and taxa might have very different vocalizations, so I acknowledge, of course, that if we're putting many different species together, then the axes of individual variation can be very different aspects, but there are always commonalities, and we can make use of that. So what Ines is doing is training a hierarchical embedding. What you see in the diagram here, we have the embeddings that I've talked about before. We can use a pre-trained system to produce a standard embedding. And then we have our hierarchical labeling. So we have our labeling that tells us which taxonomic group as well as which individual we have in the sound recording. And then this purple block here is the part that we develop a specific training regime for to produce an embedding that represents hierarchies better. The key here is to change the loss function. The loss function or cost function, that's something that we consider in deep learning. I won't go into a lot of detail about this, but basically we express numerically whether we've got a good result or a bad result. So for classification, you say the loss function says things are well categorized or badly categorized. To produce a hierarchy-aware loss function, we're actually using a kind of tree distance. So if we classify things into the wrong node on the tree, then we use a distance-based function on the hierarchy. More details in this ICASP conference paper for those who want to go into the method. But for the final example, I want to give you another thing that we work on that does, at least at the moment, use embeddings as the core tool. And this really is motivated by a really common bioacoustics question. This is something that we end up talking about whenever I've been at IBAC. Can we detect the call of the species? in these many hours of noisy audio. And here are 5 examples that I've labeled. So this is really common. And of course, many of you don't want to label thousands and thousands of examples, though you might do if you have to. But 5 examples is typically not enough to train supervised learning and get a good result. This comes up again and again, but luckily there is a paradigm that's emerged in the past few years which can handle this kind of situation pretty well. It's called few-shot learning, or sometimes one-shot learning or zero-shot learning. You may hear about this in other machine learning contexts. And the idea is to take, to develop a system, well, let's say develop an embedding that is good for use in this few-shot case. So here we developed a slightly different, well, okay, it's called few-shot sound event detection in our case. And you see it here. So we take a long audio recording and we want to label, in our case, the first 5 events in the sound file. It doesn't matter to us what these events are. They're just the 5 events that are a category of interest to you. We want to be able to put them into a system which can then tell us the rest. So far, so good, but how do we achieve that? Few-shot learning sits in this paradigm of meta-learning, which is actually quite closely related to multitask learning. It's the idea that if we can train a system that gives good performance across multiple different data sets, using the same setup as illustrated in the diagram here. So we're now not training for this one specific task, so bird call detection or mammal call detection, but we're training across all of these tasks and gradually optimizing to one single system that's pretty good at most of them. Then we produce an embedding which we can use for unseen tasks and do the same thing. This is, we launched this as a data challenge. We did it last year and we also run it again this year. And so for this year's example, here's what we provide to people attempting this task. So we have training data, we have data sets from birds, data sets from mammals that have been labeled in the same way as I showed on the previous slide. Now, the validation data for testing your own setup, we have birds and mammals, but we also have insects and various other multi-species data. And the evaluation data, well, that's a secret because it's a public challenge and we're presenting the results of that in the DCase workshop this November. But you can see just from the validation data that if you're expected to use this bird and mammal data to train a system that is able to detect mosquito sounds, for example, that's quite a difficult challenge. And clearly you can't do it just by supervised learning. One simple thing you could think about is to fine tune. So you take a pre-trained model, take all of this training data about birds and mammals, and you could say, okay, as soon as we receive 5 examples of my insect sound to detect, I'm then going to run a second round of training to sort of tweak my deep learning system to be good at this category. It feels like it should work because the system is pre-trained with a lot of general intelligence, and then we do a bit more training to sort of drag its attention towards this particular category. In practice, it doesn't work that well, and that's partly because there is still the risk of overfitting. So we're still at the end just training a system on only 5 examples, and that's a classic risk in machine learning, that you then specify to those 5 examples without good generalization to other examples of the same category. So unfortunately, this relatively simple approach doesn't work that well. Next, I want to show you the method that has been used by quite a few people, and it does work well. Now, prototypical networks is the idea here, and prototypical, so prototype. We're going to change the loss function again. So I said before, for hierarchical learning, we use a loss function that produces hierarchical information. Here, we use a loss function that is, again, not directly about classification. we want to create good centroids in our embedding space. So imagine here I've got 5 bird calls, and over here I've got 5 mammal calls, and I want to train a system where if these are all of the same category, I want to produce a good centroid. So I map the audio into this embedding space, then I take the average coordinate to produce this centroid. I do that for any of the categories I've got in mind. Now, the training process from this point onwards tries to train it so that if I put an arbitrary point into this embedding space, that it is going to cluster well to the correct group. And so what that means is the clusters, of course, have to be quite tightly packed relatively, and the clusters are distant from one another. So again, it's a distance-based training rather than a classification-based training. Prototypical networks is the sort of common term that is used to refer to this method of training. So we applied this in our baseline for a bioacoustic sound event detection, and it works well. So you can see in the table here that the prototypical net, it gets an F measure score across many different data sets of about 30%. So there's still a lot of room for improvement for sure, but if you compare it against the classic methods, energy detection or template matching, they get really bad results. And you can see that that's because, you know, energy detection, template matching, they are not bad when you're developing them for a very specific task, but here we've got very diverse and of course noisy audio data. So this prototypical net using deep learning is working well, but this is our baseline system which we've made available. And now what you see is the strongest results from the participants that submitted their own versions or their own solutions to the task. I won't go through this table in detail. I just want to point out firstly that out of these top 10 performing systems, prototypical networks were used by the majority of participants. And again, that the CNN is the basic method being used. So as I said near the start of the talk, CNN's data augmentation, those are still very good bets for when you want to do general purpose machine learning on spectrograms. So for this few-shot learning task, I do want to emphasize that there is a very large organizing team. I haven't named them here, but please visit the website to see everyone. It's because, of course, we have lots of diverse data sets. And so, of course, this is not possible to run this type of task with just a small team or just 1 or 2 data sets. So really grateful for everyone who's been part of this, helping to shape and to coordinate that task. So in my final couple of slides, I just want to point to the future a little bit, but we've talked about embeddings as a sort of core method of modern deep learning. And I've presented 2 ways that we've used it. We've used it for hierarchical classification and for few-shot classification, or few-shot sound event detection, I should really say. So here in my own place in the Netherlands, we're working on deploying bioacoustic AI. This is not really directly connected to what I've been talking about, but I just want to sort of paint a picture of where we're going. In the Netherlands, we're working on a program called ARISE, which aims to monitor all Dutch multicellular species. So that's a really grand ambition, and we're using sound recognition as part of that. We're also part of European projects to monitor many different taxa across a very large spans of Europe. So these are large-scale projects, and so we do have large data sets. We do have supervised classification, but some of the methods that I've been talking about here will feed into these. And so this is some of the work that is ongoing in our lab here. Looking forward to IBAC 2023. I'm certainly looking forward to it. I'll make a couple of risky predictions. So CNNs and data augmentation, I think we'll see those. I think it's rare nowadays to train purely from one data set. Of course, I've been emphasizing this throughout my talk, but I think a lot of work that you'll see using deep learning will be using perhaps pre-trained models, embeddings perhaps, and multitask trained systems. There will, of course, be some interesting specialist methods, and I look forward to talking about the methodology with people in various forms. But finally, to close, I do want to give credit for most of the work that I've been presenting in this talk is the work of my two PhD students, Ines Nolasco, who has been working on the hierarchical classification for individual ID, and Ines and Shubhra Singh together are the main coordinators for the DCASE Few Shot Challenge, which we've been running last year and this year. And of course, as I said, that challenge involves many collaborators, so thanks to those as well. And thank you for listening.